Hello students, the final topic of this course is the systems of linear ODEs. It corresponds to chapter 9 of our textbook, and we are going to cover it through two lessons, lessons 14 and 15. Lesson 14 is the essential part. Okay, let's begin. The systems of linear ODEs, and we have to start somewhere, so let's begin from the simplest possible case. The first order system written in the standard form. It looks like this. We have n equations, first line, second line, all the way up to last line, and then we have n functions to determine, y1, y2, y3, all the way over to yn. And then everybody can see that this is the first order system because we have only the first derivatives. No second derivative, no third derivative, nothing like that. So this is clearly the first order. And now, do you see this is linear? We have only the first degree terms, a1, y1, a2, y2, a3, y3, and so on. No square, no cube, nothing higher degree, no transcendental, no radical, and so on. So it's linear, only first degree, plus 0 degree part, which we call non-homogeneous part. Now, all these are 0. If f1, f2, f3, all these are 0, then we call this system homogeneous. If there is at least one non-zero, then this is non-homogeneous. This kind of thing is called the standard form. And the standard form can be written like this in terms of matrix expression. Do you see the correspondence? This part, we have a1, y1, a2, y2, those kind of part can be written as a matrix multiplication, a times y, where a is n by n square matrix and y is the column vector, n-dimensional column vector. And then we have another n-dimensional column vector function here for the non-homogeneous part. And then we can simplify it further into this, where A is this n by n matrix, y is this column vector function, and f is that column vector function. So compare this and then the final form. The latter part is a lot simpler than before, isn't it? And yes, simplicity will actually help. Now, as for solving this system, let's postpone it. Let's think about some theory of linear operators here. It is possible to simplify this even further like this. Subtract away, and then we can rewrite the same system like this. And then we can re-express the left-hand side using the differential operator, d minus a, where d is a derivative operator, which does this, and a is just multiplying matrix A, and it does that. So if I define my L as d minus a like this, then this whole expression, which is equivalent to that, as a matter of fact, I should have been saying this whole expression, which became that, can be simplified even further to this. L of y equals to f. And right hand side is 0, then homogeneous. So compare this. This simple expression came from this. A lot of improvement. Even more so, please note that this is just another linear operator expression, so we can recycle all those theories about linear operators that we went through in chapter 4, chapter 3 and chapter 4, like this one, homogeneous versus non-homogeneous system. For example, if you want to find out the general solution of a non-homogeneous system, this is what we do. Find out the general solution of the homogeneous system plus a particular solution. Exactly the same thing applies for the systems of first order linear ODEs because the linear operator applies here. It can be simplified into a single linear operator, so you can apply the theory of linear operators. We went through that in chapter 4. The detail is left to the students. And another conclusion from chapter 4, the principle of superposition. Let's suppose we have two non-homogeneous parts, f1 and f2, added together like this. Then basically we can add up two particular solutions, y1 and y2. That's called principle of superposition, and if you continue this, then you can have not just 2, but 3, 4 arbitrary number of non-homogeneous parts added together. Personally, I'm not really a fan of this principle of superposition, but it comes from the theory of linear operators anyway, so we went through those. Okay, so much for the review on chapter 4. Let's go over to some concrete example problem, because you see, we just went through the theory here. This becoming that, eventually generating something much simpler like these. But we went through only symbolically. So let's do those with some concrete example. But for concrete example problem, we have to do some real computations, so we have to keep it simple. Let's keep it simple. Let's do it only two functions, y1 and y2. You'll appreciate it. Okay, please recall that this system can be rewritten like this in terms of matrix expression. Oh, by the way, this is homogeneous case. I don't have any plus f1 plus f2 here. So this is homogeneous case. So we have just matrix expression, matrix multiplication, and then no plus f here. Now your goal is to verify that these are actual solutions of the original system, either this form or that form. No sweat. All you have to do is just plug those in. In the end, that's basically what I did in solution 1 here. This is so trivial that you can do it really quickly, so alright, please allow me to speed up. This is the original equation, and then y1 is e to the 2t power, y2 is also e to the 2t power, so plug all those in. This is a derivative, that too is a derivative, and here plug in, plug in, plug in, plug in all those 4 places, and then we have this system. Now, is this true? Do some algebra? Yes, it is true. What if y1 is e to the negative t power and then y2 is 4 times e to the negative t power? Well, here's the original system here, and then plug those in. This is a derivative by chain rule, and that is a derivative. And then plug in, plug in, plug in, plug in, and do some simplification. Yes, true, which means these are solutions. Did I move too quickly? Well, if you think I moved too quickly, then you can stop this playback and do some computation on your own. But this is so trivially elementary that I don't think it's really necessary. How about the second solution? We're going to do exactly the same thing, but this time let's use the matrix expression like this. So here we go, we have the original equation in matrix expression, and then let's use matrix expression and take the derivative. So take the derivative of these exponentials. We have these by chain rule. Yeah, exponentials stay the same, and we have multiplied the derivative of the inside. And then here we have to do this matrix multiplication. First row times this column, which gives me that. Second row times the column, we're going to get that. And then, is this true? Well, it's the very same computation we did earlier. This computation here, generating that. Or you can easily check on your own. You can check the other one as well. Take the derivative, and then we get this. And then the matrix multiplication. We get that, and then compare. Is this true? Check. Yes, true, of course. So we successfully verified that these two are solutions. Now here we go. Verify the general solution of the system is, well, like this. How do we do that? Let's take the same viewpoint, solution 1, and forget about the matrices, and then y1 or y1 is c1 e to 2t power, and let me rewrite. 1 is c1 e to the 2t power plus c2 e to the negative t power, and y2 is c1, same c1 e to the 2t power plus c2 4 times c2 e to the negative t power. Did I get it right? First line, second line, so first line, second line, and then you can plug those into the original system. And that computation is here. So here's the derivative computation. Also the derivative computation. So y1 prime, y2 prime. And then in the right hand side, we plug in y1, y2, y1, y2 like that, and then check. Break out parentheses and compare. Eventually, yes indeed. Did you follow? Well, if it is too quick, then you can stop this playback and then do your computation on your own. But come on, this is really, really elementary computation. So I don't think this is really worthy of our class time. But in any case, yes, you can do it. But there's a problem. This solution is incomplete. With all these tedious computation, this is incomplete. Why? Because we checked. This is a solution, yes. I mean, this pair is a solution, we checked, yes. But then again, do we get the general solution here? Are there really nothing else? We didn't do that. So this solution, despite all these computations, all this tedious computation, this is an incomplete solution. Now let's go to the next expression. This will be a complete solution. And complete solution looks that simple. We just use the theory of linear operators. We have a pair of solutions that are linearly independent. So simply take the linear combination and voila, that's the general solution. It's just one-liner. Maybe you'll have to check whether these two are really indeed linearly independent, but even that is one-liner or maybe less, because if you have 3 functions, then checking those can be a bit tricky. But if you have 2, then all you have to check is whether they are collinear. Now, is this thing constant times that? No way. We have 2 different exponentials, so that's completely impossible. So it doesn't even require even a single line, but maybe if you want to add more, let's see. Given pair of solutions are linearly independent, they are not collinear. Okay, that's sufficient. Therefore, taking the linear combination of the 2, we get the desired expression immediately, and there. Okay, all right. Previously, I didn't have this line. I just added to make it even better. But then again, these are all, some subscript or superscript kind of thing. The essential part is here. If you use the theory of linear operators, then you can answer the problem a lot more effectively than doing tedious computations like this. So here, doing line by line separately versus using matrix expressions and using the theory of linear operators was kind of push. But here, no contest. This one really complicated but still incomplete. This one on one-liner basically, maybe two-liner, yet complete. So I really encourage you to go through these matrix expressions. And in the next example, I'm not going to do the individual lines. I'll just go directly to matrix expressions only. All right, let's go to the next example here. This time, the same system, except we have non-homogeneous part. The linear part is the same, never mind. This was the previous system. So linear part is the same, but we have non-homogeneous part. And then the matrix expression goes like this. Same part here, and then we have non-homogeneous part. Verify the following pair of functions is a solution. Okay, all right. Plug those in, take the derivatives, and then check those out. Well, here's the original equation. I just copied it from here, basically. And then we take the derivative. Take the derivative -2, -4. That was easy. And then this is a matrix multiplication. Here we have y1 and y2. So we multiply first line, column, and that's going to be up to here. And then we have plus 2t, the non-homogeneous part. Second line, and this column, and it's going to be up to here. And then we have this plus 2 from this non-homogeneous part here. And if you simplify, yes, the answer is yes. Checks out. So yes, it is a solution. So if you have a candidate of a solution, then checking whether it's a solution or not is easy. We just did that, and then finally verify the general solution of the system is like this. I didn't even bother writing any solution here because it doesn't even require that. We need the general solution of the homogeneous part plus a particular solution, and that's it. And what did we use? We didn't use any fancy computational technique. We just used, oh, not this one. We just used the theory of linear operators, this one.